In the earlier lecture in part 1, we mentioned certain topics which were probably taught to you, some of them in high school, some of them in first year BTech, and so on. We propose to cover these topics more from the point of view of highlighting certain important aspects of these topics. Entropy is always increasing. It is the nature of the universe to go from bad to worse. But this is thermodynamics. It's been taught to us in first year college. But do we know the impact of entropy in physics? Yes, damping. When you were taught vibration, you were taught that there are three components to a vibrating system: the stiffness, the damping, and the inertia. The damping is non-recoverable side. Once whatever energy goes in, it can never be recovered. Next, conservation of mass. Conservation of mass is something we'll be dealing with an example shortly. So I'll just say that mass can never be created or destroyed. It is a constant. Given the system to begin with, the mass in the system remains a constant. Conservation of energy. Conservation of energy again is a simple principle, which is an idealism. It says that potential energy plus kinetic energy is a constant. It does not take into account non-recoverable losses. Some phenomenological laws or Newton's laws, Ohm's laws, Kirchhoff's law, these are all laws which are true as the sun coming up in the east every morning. However, they cannot be theoretically verified. They can only be experimentally proven. When you press on an object, the object pushes back at you with the equal force as long as the object is not moving. This is Newton's third law in action. Action produces reaction. But can you prove that theoretically? No, you cannot. Similarly, take an electrical circuit, apply a certain voltage, pass a certain current through the circuit. If it has a certain resistance, the three factors will be related according to Ohm's law. Similarly, Kirchhoff's law, the sum of currents coming onto a node will be equal to the current that is going out of the node. Conservation of mass is something that we just addressed. Conservation of energy has also been just mentioned. Superposition principle. Now, this is a very, very interesting concept. But before we go in depth into superposition principle, we must understand something. In reality, nothing in life is actually linear. Everything is non-linear. But since we are ready to accept an approximation as a solution, we are able to linearize it. What is the impact of linearity? Well, your approximation may be 80% approximation or 90% approximation or even 95% approximation. Seldom more than that. It is the path that is left out is the loss due to ignoring nonlinearity. So, superposition principle works. It's a concept that has been created. It works only within the gamut of linearity. That is, if you have a system and you apply an input A, for instance, if you have a spring and you hang 2 kilos below the spring deflects to say 1 inch. Then you hang 4 kilos below the spring and it hangs 2 inches. Then you know for a fact that by scaling the first one, you can get the second one. So the input A plus B will produce the response X plus Y. This is known as superposition. Superposition gives you implied linearity, which is a prior assumption, and it also gives you scalability. Wikipedia is something that I don't normally encourage as a reference, because Wikipedia is meant for all kinds of people and all levels of expertise. Consequently, being jack of all trades, it ends up as being master of none. Specific data cited inside Wikipedia is always good because it comes from standard references such as sometimes tables which are internationally accepted, which are international standards. However, verbal definitions, one has to be very careful taking Wikipedia. We must always remember that Wikipedia is very good at presenting the feeling of a subject than it is of the specific definition. Whenever I learn something new, I do not mind going through Wikipedia for the first time. But when I start going deeper and deeper into a topic, I avoid Wikipedia. In this case, superposition principle is demonstrated beautifully inside Wikipedia with a graphic. This involves a rolling wheel which consists of rotational and translational motion. The rolling wheel's motion can be cut into rotation and translation, and when the two are added together, one gets the rolling motion. This is the real application of superposition principle. The next one you're going to look at is something called point mass. Can a point have mass? The definite answer from all of you, I'm sure, is no. But however, old days physics people have created a concept called point mass. Now, I cannot draw a point on a sheet of paper which has got zero width, because if it has zero width, technically it doesn't exist. So we define point mass as a point of infinitesimal size, sort of like delta x tending to zero. It is an approximation used for convenience when you linearize a system, as you will see once we get going with the course deeply. Its most defining feature is that while the point itself has no spatial existence by way of length, breadth, or height, or diameter, or radius, it has a non-zero value of mass associated with it. And it is at best a physics definition, nothing more than that. The only feature that it has is mass. And take, for instance, a shaft in a mechanical system. This shaft may have possibly a 10 kilogram load acting at one end. Now, if I were to look at this as a physical object, I'll have to draw the shaft and apply the 10 kilogram load at one end. But if on the other hand, I'll have to look at it as a point mass, I need to find the center of mass of this shaft and just apply the 10 kilogram load there. The fact that it is at one end is no longer significant once I have made the point mass assumption. Where is it useful? It is useful in the formulation of many problems, and I'll show that to you. A simple example, earlier we spoke of a motorcycle being modeled as a spring and damper system with a mass hanging below. Such an assumption is possible only because of point mass. Linearity. Linearity is again something that is an approximation within an approximation. Linearity is probably the greatest approximation one ever makes in maths, because it makes all sorts of equations solvable. If not for linearity, there will be no solved equations. Linearity provides additivity and scalability. In fact, in reality, linearity is nothing more than superposition principle. It is linearity which makes superposition principle possible. A behavior which is characterized by an equation such as Ohm's law is a linear relationship. Some basic skills you will need in system identification and design. One of them is to be familiar with mechanical systems. When one looks at a pump on a borewell in a house, you should be able to recognize the component parts intuitively. It has a shaft, a motor, an impeller which draws the water from underground. Similarly, when you look at a motorcycle, you recognize the fact that it's got tires, shock absorbers, electrical system, and an engine and a transmission. You need a knack of knowing how things work. Such a knack could be very useful. And when you look at a system, it is useful to know how the subsystems are put in place and where do they begin and where do they end. For instance, in a car, an electrical subsystem may involve all the electrical wiring and battery and all that, and even the dynamo. But the power for the dynamo to start, that comes from outside. You need to know the borders of subsystems. Probably one of the most relevant skills to have would be a thorough grounding of basic calculus and ability to solve first order and second order differential equations, both of the homogeneous variety and the non-homogeneous variety. Basic references, any book on basic mechanics, if you can look up the first 2-3 chapters, could be very useful. And like I said earlier, look up Wikipedia under point mass, superposition principle, or linearity. Thank you.